A single star can hold our entire solar system within its fiery borders. These are the universe's most massive stars, celestial titans whose lives defy imagination. By the end of our journey, you will understand how these giants literally built the world you live in. We will uncover why they live such explosively short lives and what mysterious force prevents them from growing even larger. What do you believe is the most profound legacy a star can leave behind to even qualify as a massive star? A celestial body must begin its life weighing at least 8 times more than our own sun. This is not merely a matter of being a larger version of the friendly yellow star we know. It marks the entry point into an entirely different class of stellar existence, governed by more extreme physics and destined for a far more dramatic fate. While our Sun is a stable, long-lived main sequence star, these giants are cosmic titans living on borrowed time. Their immense mass creates such crushing pressure and ferocious heat in their cores that they burn through their nuclear fuel at a staggering, almost wasteful rate. At the very top of this scale, we find the true behemoths, stars so colossal they push against the very laws of physics. The most massive stars ever observed tip the scales at over 200 times the mass of our Sun. These are not just stars, they are forces of nature, testing the theoretical limits of how much material can possibly be gathered into a single, shining point. This incredible mass does not come without a cosmic price. There exists a fundamental ceiling, a point where a star's own brilliance becomes its greatest enemy. This boundary is known as the Eddington limit, a theoretical wall that prevents a star from growing beyond approximately 150 to 200 times the mass of our Sun. The physics behind this limit is a beautiful and violent balancing act. Deep within these titans, the furnace of nuclear fusion burns with unimaginable ferocity. This process does not just create light, it creates an immense outward radiation pressure, a constant, powerful wind of pure energy streaming from the star's core. For a star to grow, it must pull in more gas and dust from its surroundings. But once a star approaches that critical mass limit, the radiation pressure pushing outward becomes so overwhelmingly strong that it overpowers the star's own gravitational pull. It literally starts blowing its own building materials back into space. The star is caught in a futile cycle, trying to eat a meal while a hurricane-force wind blows the food off its plate. This is why we do not see stars with 500 or 1,000 solar masses. They simply cannot hold themselves together. Every massive star we find nudging that upper boundary is a natural laboratory, allowing us to test the laws of physics under conditions so extreme they cannot be replicated on Earth. They are the universe's way of showing us exactly how far its rules can be pushed. Deep within a neighboring galaxy, a star exists that defies all sense of scale. Its name is R13601, the single most massive star ever identified by humanity. It lives not in our own Milky Way, but in a spectacular stellar nursery known as the Tarantula Nebula, located in the Large Magellanic Cloud. When this colossal object was born, its initial weight was almost incomprehensible. Astronomers estimate it began its life with a mass somewhere between 196 and 315 times that of our Sun. This places it right at the theoretical edge of what is possible, a true test subject for the Eddington limit we just discussed. Even now, after shedding vast amounts of its own substance, it remains a behemoth. But its mass is only part of the story. The true measure of this star's power is its luminosity. R13601 does not simply shine, it rages with the energy of nearly 9 million of our suns combined. To put that into perspective, if you could place this star at the center of our solar system, its blinding light and intense radiation would utterly vaporize every planet out to the orbit of Jupiter. Its surface temperature adds to its ferocious nature, blazing at over 100,000 degrees Celsius, which is more than 10 times hotter than the surface of our own Sun. This is not a gentle giant, it is a celestial furnace operating at its absolute limit, a raging inferno whose very existence teaches us about the ultimate extremes of stellar life. This staggering power comes at a devastating cost. A star like our Sun is a model of cosmic stability, destined to shine gently for 10 billion years or more. But the most massive stars live by a different, more violent creed. They burn through their entire supply of nuclear fuel in a cosmic blink, lasting just a few million years. To grasp this difference, think of a single candle burning steadily in a quiet room. It could glow for dozens of hours, providing a soft, consistent light. Now picture a massive firework being ignited. For a few breathtaking seconds, it erupts in an incandescent blaze of color and sound, outshining everything around it before vanishing completely. That is the life of a massive star, a glorious, fleeting firework against the long, dark night of cosmic time. The reason for this rapid burnout lies in the star's own immense gravity. All that mass is pulling inward with unimaginable force, crushing the core and superheating it to temperatures far beyond our suns. This creates a pressure cooker of epic proportions, forcing the nuclear fusion process to run at a frantic, unsustainable pace. While our Sun fuses hydrogen into helium at a calm, measured rate, a massive star is a runaway reactor, consuming its fuel with a desperate, furious hunger. It is not merely burning its hydrogen, it is devouring it. This furious consumption dictates every moment of its short, dramatic life, a race against its own inevitable collapse. These cosmic titans are not born in quiet solitude. They emerge from the most chaotic and dense regions of vast stellar nurseries, known as giant molecular clouds. These are not mere collections of gas, but dark, frigid, and turbulent structures so immense they could swallow entire star systems. Within these cosmic wombs, the densest knots of gas and dust begin to collapse under their own gravity, but for a massive star, the process is anything but peaceful. It is a violent, competitive free-for-all. Unlike a star like our Sun, which forms in relative isolation, the most massive stars almost always form in tight-knit clusters, surrounded by hundreds of sibling stars. In this crowded nursery, the race for mass is fierce. The largest protostars engage in a process called competitive accretion, where their stronger gravity pulls in more gas from the shared reservoir than their smaller neighbors. They grow fat while others starve, becoming the bullies of the birthing cluster. This formative chaos is marked by powerful outflows, colossal jets of material that scream outward from the infant star's poles as it feeds. Even as it gathers mass, it is already throwing a portion of it back into space with tremendous force. But the true impact of a massive star begins the moment its nuclear furnace ignites. It immediately begins to reshape its entire neighborhood. Its intense ultraviolet radiation is so powerful it ionizes the surrounding hydrogen gas, blowing vast, glowing bubbles of plasma into the cloud. Simultaneously, its fierce stellar winds, a relentless stream of charged particles, slam into the remaining gas and dust like a cosmic hurricane. This dual assault has a paradoxical effect. On one hand, it can compress nearby pockets of gas, triggering a new wave of star formation by pushing them over the edge of gravitational collapse. On the other hand, that same ferocious energy can shred and disperse the very cloud that gave it birth, blowing away the building materials for future stars and effectively shutting down the nursery. A massive star is both a creator and a destroyer, the ultimate architect of its own stellar destiny and the fate of every other star nearby. This furious consumption is made possible by a different kind of engine entirely. Deep within our own Sun, the process that converts hydrogen into helium is called the proton-proton chain. It is a relatively slow, methodical dance of particles, perfectly suited for a star of modest size and temperature. But inside the core of a massive star, where temperatures soar to staggering heights, a far more powerful and efficient process takes over. This is the carbon-nitrogen-oxygen cycle, or the CNO cycle for short. Think of it as the difference between a campfire and an industrial furnace. The proton-proton chain is that steady campfire burning logs one by one. The CNO cycle, however, is a high-tech furnace that consumes its fuel with a voracious, explosive intensity. Its efficiency is breathtakingly sensitive to temperature. For every single degree the core heats up, the rate of fusion in the CNO cycle skyrockets. This creates a powerful feedback loop. More fusion makes the core hotter, and a hotter core makes fusion happen even faster, driving the star's energy output to unimaginable levels. This is the primary reason these giants shine with such ferocious brilliance, outshining our sun by millions of times. But the legacy of this cycle extends far beyond raw power. The CNO cycle is not just a consumer of hydrogen, it is a cosmic factory. In its frantic, multi-step process to create helium, it uses atoms of carbon, nitrogen, and oxygen as reusable catalysts. These elements are constantly being transformed from one to the other and back again in a rapid, endless loop. This churning, high-energy environment is responsible for forging the majority of the universe's nitrogen and oxygen. Every breath you take contains atoms that were once forged in the heart of a long-dead massive star, created within the very same fiery process that gave it such a short, spectacular life. This frantic energy output is not a random trait, it is a fundamental law of stellar existence. The relationship between a star's mass and its brightness is one of the most powerful and predictable rules in all of astronomy. Known as the mass-luminosity relation, it reveals a staggering truth. A star's luminosity is not simply proportional to its mass, but to its mass raised to the power of 3.5. This mathematical exponent holds immense consequences. It means that if you were to double a star's mass, its brightness would not merely double, it would increase by a factor of more than 10. But the real magic, or perhaps the real terror, happens when we scale up to the true giants. Consider a star that is 10 times more massive than our Sun. You might expect it to be 10 times brighter. The reality is far more extreme. That 10 solar mass star would actually shine with the light of approximately 3,000 suns. Now push that further to a star like R13601, which is over 200 solar masses. That exponent of 3.5 works its incredible math, transforming its immense bulk into a beacon of nearly 9 million solar luminosities. This is the core reason why these rare, massive stars completely dominate the ecology of their galaxies. In a cluster containing thousands of smaller, sun-like stars, the light from a single massive titan can outshine all of them combined. They are the brilliant, short-lived monarchs of the cosmic landscape, their overwhelming light dictating the energy flow and chemistry of entire stellar nurseries. Their brilliance is not just a spectacle, it is the direct and inevitable result of the crushing weight they must bear. This overwhelming brilliance comes with a constant, tangible cost. A massive star does not simply radiate light, it physically throws its own substance out into the void. The surface of a star like R13601 is a maelstrom of ferocious activity, where the outward pressure of its own radiation is so immense it acts like a continuous, powerful gale. This is the force behind stellar winds, and for these titans they are anything but a gentle breeze. These are billion-degree hurricanes of charged particles, screaming outward at millions of kilometers per hour. Compared to the solar wind from our Sun, which is a mere whisper, the stellar wind from a supergiant is a constant, deafening roar. It is the star literally trying to tear itself apart from the inside out, its own light pushing its outer layers into space. This process of mass loss is not a minor event, it is a fundamental part of the star's life cycle. A star can shed an amount of material equal to the entire mass of our Sun in just 100,000 years. To grasp that scale, our Sun has existed for 4.6 billion years and has lost only a tiny fraction of its total mass. These giants are on a cosmic diet of the most extreme kind, violently expelling their own bulk in a desperate attempt to manage their impossible internal pressures. This constant shedding does more than just shorten the star's life by depleting its fuel reserves. It actively seeds the cosmos. The material blown away in these powerful winds is not just hydrogen and helium. It is enriched with heavier elements forged in the star's frantic core, elements like carbon, nitrogen, and oxygen. Every gust from this celestial hurricane sprinkles the surrounding space with the very building blocks of future planets and potentially life itself. The star is both a creator and a sacrifice, using its own body to fertilize the galaxy for generations to come. This ferocious energy loss carves a very specific and extreme identity for these stars on the most important chart in all of astronomy, the Hertzsprung-Russell diagram. Imagine a graph mapping every star, not by its location in space, but by its fundamental properties of temperature and luminosity. Our own Sun sits in a quiet, comfortable region known as the main sequence, a broad diagonal band where stars spend the majority of their lives fusing hydrogen. But the massive stars we have been discussing do not live in that calm neighborhood. They are exiled to the diagram's most extreme upper left corner, a place reserved for the hottest, brightest, and most volatile stellar objects in the universe. Here we find the O-type and B-type stars, the brilliant blue-white aristocrats of the cosmos. Their position is no accident. Their immense luminosity places them at the very top of the chart, shining brighter than almost any other star. And their searing surface temperatures, which can soar beyond 30,000 Kelvin, push them far to the left into the realm of the most intense stellar heat. This combination of incredible brightness and blistering temperature gives them their characteristic blue-white hue. Just as a metalworker's torch burns blue at its hottest point, these stars glow with a searing sapphire light, a direct and visible testament to the nuclear inferno raging within them. Their light is so intense and so rich with high-energy photons that it does not simply pass through the surrounding gas, it fundamentally alters it. The spectra of these stars, the unique chemical fingerprints obtained by splitting their light, are dominated not by the simple lines of neutral hydrogen, but by the signatures of ionized helium and other heavy elements that have been stripped of their electrons by the relentless ultraviolet barrage. To look at the spectrum of an O-type star is to witness the signature of pure, unbridled power, a celestial environment so harsh it tears matter apart at the atomic level. This searing blue-white light is more than just a spectacle, it is a direct consequence of the star's chemical recipe. The very ingredients a star is born with fundamentally shape its destiny, a concept astronomers call metallicity. In the language of the cosmos, metallicity has a specific meaning. It refers to the abundance of every element heavier than helium. This includes oxygen, carbon, nitrogen, and iron, everything that is not hydrogen or helium, the primordial stuff of the Big Bang. For a massive star, this chemical composition is not a minor detail. It is a critical governor on its life and death. A star born from a cloud rich in these heavier elements, a high metallicity environment like our own galaxy, faces a unique challenge. Those metal atoms are incredibly efficient at absorbing the star's intense light. When a photon of light is absorbed by a metal atom high in the star's atmosphere, it gives that atom a tremendous kick, propelling it outward into space. This process supercharges the stellar winds we discussed earlier. The higher the metallicity, the more efficient this engine of mass loss becomes, leading to a constant, powerful bleeding of the star's outer layers. This relentless shedding can act as a cosmic brake, preventing a star from ever reaching its theoretical maximum mass, no matter how much gas it originally gathered. It is a paradox. The very elements that make planets and life possible also serve to limit the growth of the universe's most spectacular stars. This leads us to a profound and mysterious thought. What would a star look like if it were born from a perfectly pure cloud, one completely devoid of these heavier elements? To find that answer, we must look back to the very dawn of time, to the first generation of stars. These hypothetical objects, known as population 3 stars, are thought to have formed from nothing but hydrogen and helium. Without any metals to drive powerful stellar winds, they could have grown to truly monstrous proportions, potentially reaching masses of several hundred or even 1,000 times that of our Sun. Their lives would have been unimaginably brief and violent, ending in cataclysmic explosions that, for the very first time, seeded the universe with the metals that would one day build everything we see around us. We have never directly observed one of these primordial giants, but their theoretical existence solves a cosmic mystery, explaining how our metal-rich universe was built from a beginning of absolute purity. Peel back the outer hydrogen layer of a dying supergiant, and you will find a cosmic onion of immense complexity and violence. This layered structure is not a static arrangement, but a frozen record of the star's desperate struggle for survival. As we journey inward, each concentric shell tells the story of a different nuclear fire, a different stage in the star's frantic consumption of its own fuel. The outermost envelope, a vast and turbulent sea of hydrogen, is the last remaining reservoir of the star's original substance. Just beneath it, nuclear fusion is actively converting this hydrogen into helium, the same stable process that powers our Sun. But here, it happens on a scale of epic ferocity. The helium produced in this shell does not simply accumulate, it sinks inward, crushed by the immense weight of the layers above it. As we descend further, the temperature and pressure skyrocket. We pass through a distinct layer where the primary fuel is no longer hydrogen, but the helium ash from the shell above. Here, under even more extreme conditions, helium nuclei are forced together in a process known as the triple alpha process, fusing to create carbon. This is the star's second engine, burning directly below the first. And the pattern continues. The carbon produced in this fusion sinks down, piling up until the core becomes hot and dense enough to ignite carbon fusion itself. This process forges even heavier elements like neon and oxygen. Each new layer represents a new chapter in the star's life, a new fuel source ignited out of sheer gravitational necessity. The neon layer ignites, then the oxygen, and finally, at the very center, a shell of silicon begins to burn. The silicon atoms fuse, link by link, in a frantic nuclear chain reaction. But this is where the star's journey of creation meets a catastrophic dead end. The final product of silicon fusion is iron, and iron is nuclear ash in its most stable, most inert form. To fuse iron atoms together does not release energy, it consumes it. The star's central engine, after burning brilliantly through a succession of fuels, has finally created a core that can no longer support it. The star has, in its final moments, built its own tomb. This layered architecture is a ticking time bomb with a core of iron that spells the end for the entire colossal structure. Iron is the silent killer lurking in the heart of a giant. For millions of years, the star has battled its own gravity with the power of nuclear fusion, each new element providing a fresh burst of outward pressure. But when silicon fusion finally forges iron-56 in the core, that battle is lost. This specific isotope of iron is the most stable, the most tightly bound atomic nucleus in all of nature. That stability is a death sentence. Every previous fusion reaction, from hydrogen to helium and from helium to carbon, released a tremendous surge of energy. This energy created the pressure that held the star up, like a powerful spring countering the crushing weight of its own outer layers. Fusing iron, however, works in reverse. It does not release energy, it demands it. It is a nuclear reaction that acts like a power drain, sucking thermal energy directly out of the star's core. In an instant, the star's central support system vanishes. The outward pressure that has sustained it for its entire life simply winks out of existence. After a lifetime of brilliant defiance, gravity finally and catastrophically wins. With nothing left to push back, the core has no choice. It begins to fall inward under its own unimaginable weight. This collapse is not a gentle settling. It is a free fall that accelerates to a significant fraction of the speed of light, as a core with more mass than our entire sun crushes itself into a sphere barely the size of a city. The stage is now set for the universe's most violent performance, a supernova explosion. The collapse of an iron core is the ultimate act of cosmic betrayal. For millions of years, fusion provided a steady outward push against the star's own immense gravity. But iron fusion consumes energy instead of releasing it, and in that single moment, the star's central support vanishes. Gravity, held at bay for so long, becomes an unstoppable force. The core, which moments ago was a sphere roughly the size of Earth, is now in free fall. It collapses inward at nearly 1/4 the speed of light. In less than a single second, this colossal object is crushed into an unimaginably dense sphere only about 20 kilometers across. The densities reached in this catastrophic implosion are beyond human comprehension. The matter is squeezed so tightly that atoms themselves are destroyed. Electrons are forced into protons, transforming them into neutrons and releasing a flood of ghostly particles called neutrinos. For a fleeting moment, the entire core becomes a single, solid ball of neutrons, a neutron star in its raw, nascent form. But the collapse does not end quietly. The inward rush of material is so violent and sudden that it overshoots this new state of equilibrium. The core becomes rigid, and the still infalling outer layers of the core smash into this newly solid surface. The result is a titanic rebound, a powerful shockwave carrying the energy of 100 suns exploding every second for 1 billion years, ripples back outward from the core. This shockwave is supercharged by the very neutrinos just created, which deposit a colossal amount of energy into the blast. This combined force is more than enough to overcome gravity's grip on the star's remaining layers. The star does not just explode from the inside out, it is utterly obliterated. The entire outer structure of the star, all those complex layers of hydrogen, helium, carbon, and oxygen, is blasted into the void at tens of millions of kilometers per hour. This is a core collapse supernova, a flash of light so brilliant it can, for a few weeks, outshine an entire galaxy of 100 billion stars. In this single, violent event, the star completes its final and most important task, scattering the elements it forged across the cosmos, seeding future generations of stars, planets, and life itself. That brilliant flash is only the beginning of the story. The expanding shockwave from the supernova, now a rapidly growing sphere of incandescent gas and stellar debris, slams into the surrounding interstellar medium. This collision creates one of the most beautiful and enduring structures in the cosmos, a supernova remnant. For thousands of years, this glowing cloud will remain visible, a slowly fading monument to the star's final act. Perhaps the most famous example is the Crab Nebula, a tangled web of glowing filaments that is all that remains of a star whose light reached Earth in the year 1054. These remnants are more than just celestial ghosts, they are cosmic cauldrons. Within their turbulent, shock-heated gases, temperatures and pressures remain so extreme that they can forge elements even heavier than iron, like gold, silver, and uranium, completing the periodic table that the star itself could not finish. Yet, while this glowing cloud marks the star's grave, it is not the only legacy. At the very heart of this expanding chaos, the collapsed core of the star remains. If the original star was between 8 and roughly 25 times the mass of our Sun, that core does not become a black hole. Instead, it transforms into one of the universe's most bizarre objects, a neutron star. Imagine taking more than the entire mass of our Sun and crushing it into a perfect sphere barely the size of a city. This is the reality of a neutron star, an object so dense that a single sugar cube-sized piece of it would weigh as much as every human on Earth combined. It is a world where matter has been compressed to its absolute limit, a place where atoms have been destroyed and protons and electrons have been forced together to form a solid ball of neutrons. This city-sized cinder, spinning rapidly and possessing a magnetic field trillions of times stronger than Earth's, is the final, incredible testament to a giant's life. For the very most massive stars, the final act of collapse does not end with a neutron star. When a star begins its life with more than roughly 25 times the mass of our Sun, the weight bearing down on its core is simply too immense for any known force in the universe to withstand. The formation of a neutron star is a desperate last stand, a state where matter is compressed into a solid ball of neutrons. But for these ultimate titans, even that incredible density is not enough. The collapse does not pause, it does not rebound. It continues unstoppable and absolute. The core, now a rapidly shrinking point of unimaginable density, simply vanishes from the observable universe. It crosses a threshold of no return, a boundary we call the event horizon. This is not a physical surface, not a solid shell you could touch. It is a mathematical point of infinite curvature, a one-way door in the fabric of space-time. Once anything, even light itself, crosses this invisible boundary, it can never come back. The star's core has become a stellar mass black hole, the direct and terrifying descendant of the universe's most massive stars. The gravitational effects near this point are profound. Time itself slows to a crawl relative to the outside universe. The pull of gravity becomes so intense that it warps the paths of light, creating a perfect black sphere of shadow against the backdrop of space, surrounded by a distorted ring of light from stars behind it. This is the final, silent monument to a giant's life, a gravitational tombstone where a star once raged. But there exists a fate even more total and violent than a black hole. For the rarest and most massive stars, those born with between 130 and 250 times the mass of our Sun, their final act is one of pure, unadulterated self-destruction. These are the pair instability supernova, and they leave nothing behind, not a neutron star, not a black hole, just an empty patch of space and a brilliant, fleeting memory. This cataclysm begins deep within the star's core, in its final helium burning stages. The temperature here becomes so phenomenally high that the photons of light themselves, specifically gamma rays, are no longer mere particles of energy. They become so densely packed and energetic that they begin to behave in a way predicted by Einstein's most famous equation. Spontaneously, a gamma-ray photon can transform into a pair of particles, an electron and its antimatter counterpart, a positron. This is not a gradual process, it is a sudden, catastrophic phase change. What was once pure radiation pressure, the very force holding the star up against gravity, is instantly converted into matter. The core's supporting pressure vanishes in a flash. Without that outward push, gravity wins instantly and completely. The core collapses inward at a breathtaking rate. But this is not the controlled collapse that forms a neutron star. The sudden, runaway compression heats the core to temperatures beyond imagination, reigniting nuclear fusion with a ferocity the universe rarely witnesses. In a single, unstoppable chain reaction, the entire core undergoes a thermonuclear explosion. It is not a rebound, it is a detonation. The blast is so powerful, so utterly complete, that it does not just blow off the star's outer layers. It tears the entire star apart from its center to its surface, scattering every single atom into the void. No remnant survives. The star simply ceases to be, vanishing in a flash of light that can outshine a small galaxy. This is the ultimate cosmic sacrifice, a firecracker that consumes itself entirely, leaving only the echoes of its elements to tell the tale. The ghost of a giant does not always rest in silence. Sometimes the neutron star left behind becomes one of the most precise timekeepers in the universe, a cosmic lighthouse known as a pulsar. This happens when a neutron star is born spinning at a dizzying rate, sometimes completing hundreds of rotations every single second. Its unimaginably powerful magnetic field, channeling energy from its rapid spin, focuses intense beams of radiation out from its magnetic poles. If these poles are misaligned with its rotation axis, the star sweeps these beams through space like the beacon of a lighthouse. From our distant vantage point on Earth, we see a flash of radio waves, or sometimes even visible light or X-rays, every time that beam sweeps past our telescopes. We call this a pulsar, a celestial metronome whose rhythmic pulse can be more reliable than the most advanced atomic clocks on Earth. But even this incredible object has a more volatile cousin. Imagine a magnetic field so intense it defies comprehension. This is a magnetar, a neutron star whose magnetic field is 1,000 times stronger still, reaching levels of 1 trillion times the strength of Earth's own field. A field of that magnitude is not merely a force, it is an active, destructive presence. It can literally twist the star's solid crust, which is a mile thick and harder than any known material, causing colossal fractures known as starquakes. These quakes release more energy in a fraction of a second than our Sun will emit in 100,000 years, unleashing titanic flares of gamma rays and X-rays that can travel clear across the galaxy, momentarily outshining every other source in the sky. These exotic objects are the final, fading heartbeats of the universe's most massive stars. Their rhythmic pulses and violent shudders are testament to the forces unleashed in their cataclysmic birth. These elements are the ultimate legacy of the giants. Every atom of oxygen that fills your lungs, every particle of iron coursing through your veins, was forged in the heart of a massive star that no longer exists. We are quite literally stardust given consciousness, the universe's way of remembering its most spectacular creations. This is cosmic recycling on the grandest scale. Massive stars act as the universe's primary foundries, the only natural environments hot and dense enough to create the heavier elements that form the bedrock of planets and life itself. Throughout their lives, their fierce stellar winds blow enriched material into the void, but it is in their final, explosive death throes that they complete their most vital work. The supernova's unimaginable energy and the frantic nuclear reactions within the blast itself forge elements even heavier than iron, from cobalt and nickel all the way up to gold and uranium. Then the expanding shockwave acts like a cosmic farmer, sowing these newly minted elements far and wide, scattering them across interstellar space. This enriched gas, now peppered with carbon, oxygen, silicon, and iron, eventually coalesces into new generations of stars, planets, and ultimately us. Our solar system itself formed from the ashes of such long-dead giants. The calcium that strengthens your bones, the silicon that forms the rocks beneath your feet, the very oxygen that makes our atmosphere breathable, all of it was a gift from stars that died billions of years ago. We are living proof that the most violent endings in the cosmos are also the most creative beginnings. Their brief, brilliant lives ripple across entire galaxies. Though these titans are incredibly rare, making up less than 1% of all stars, their influence is so profound they dictate the very life cycle of their cosmic homes. Think of a galaxy not as a static painting, but as a living, breathing ecosystem. In this grand system, massive stars are the ultimate agents of change. Their intense ultraviolet radiation does more than just light up a nebula. It carves out vast cavities in the interstellar gas, heating it to millions of degrees and preventing it from collapsing too quickly into new stars. Their powerful stellar winds act like cosmic plows, sweeping up and compressing surrounding gas into dense shells. In some regions, this compression is the final nudge needed for a cold, dark cloud to collapse under its own weight, igniting a new generation of stars. This process, called triggered star formation, means that the death of one stellar giant can be the direct cause of hundreds of new stellar births. Yet, in other circumstances, that same ferocious energy can have the opposite effect. The combined force of radiation and wind from a cluster of massive stars can become so overwhelming that it blows the galaxy's entire reservoir of star-forming gas clean away. This creates a powerful galactic wind, a river of superheated material flowing out from the galaxy into intergalactic space. This is a crucial form of cosmic regulation. By ejecting this raw material, the massive stars effectively put a limit on their own galaxy's growth, halting future star formation and shaping the galaxy's ultimate size and structure. Their final supernova explosions add the final, dramatic punctuation to this cycle. Each blast injects the energy of 1 billion suns into the galactic environment, further churning and heating the interstellar medium. More importantly, it is these explosions that seed the galaxy with the heavy elements forged in the star's core and during the blast itself. This chemical enrichment is a gradual process building over billions of years. The first stars in the universe were composed only of hydrogen and helium. It was the death of the first massive stars that polluted the pristine cosmos with the carbon, oxygen, and iron necessary for the rocky planets and life that would follow much later. Every spiral arm you see in a galaxy photograph, every vibrant nebula, and even the very metallicity that defines a galaxy's age, all of it is a testament to the enduring, galaxy sculpting power of its most massive and ephemeral stars. There is a moment in the life of a true stellar titan when it tears away its own skin. Having shed its vast hydrogen envelope through a relentless billion-year stellar wind, the star stands exposed. This is the Wolf-Rayet phase, a final, defiant chapter before the supernova. What remains is not the star we once knew, but its naked, blazing core. The surface is now a searing hellscape, hot enough to fuse helium into carbon and oxygen, and the star glows with an intense blue-white light that speaks of its imminent demise. Its spectrum, the unique fingerprint of its light, is unlike any other. Instead of the dark absorption lines of a normal star, we see brilliant, broad emission bands. These are the signatures of elements like helium, carbon, and oxygen being violently ejected from the surface at speeds exceeding 10 million kilometers per hour. The star is literally writing its own epitaph in light, a luminous scream of expanding gas that tells us it has nothing left to hide. This spectacular display cannot last long. A Wolf-Rayet star is a supernova progenitor in its final act, a cosmic torch burning at both ends. It will live like this for only a few 100,000 years, a mere blink in cosmic time before its core collapses and it ends its life in one of the universe's most brilliant explosions. Eta Carinae is a star that refuses to die quietly. It belongs to a rare and volatile class of stellar objects known as luminous blue variables, the true loose cannons of the cosmos. These are not merely large stars, they are hypergiants existing in a state of perpetual, unstable balance, perpetually on the verge of tearing themselves apart. Their immense mass and ferocious luminosity create such extreme outward pressure that their own gravity can barely hold them together. The result is a star that throbs and pulses violently, its outer layers so loosely bound that they can be hurled into space in catastrophic eruptions. Eta Carinae is the most famous of these celestial time bombs, and in the middle of the 19th century, it gave humanity a front-row seat to its instability. In the 1840s, this star experienced what astronomers now call the Great Eruption. Over a period of about 20 years, it convulsed, expelling an amount of material equal to at least 10 times the mass of our entire Sun. This colossal outburst of gas and dust propelled it to become the second brightest star in the entire night sky, a position it held for years before fading again into relative obscurity. The ejected material did not simply dissipate, it formed the beautiful and bizarre homunculus nebula, a twin-lobed cloud of gas that still expands outward from the star today, a permanent smoke ring from its greatest explosion. The driving force behind these apocalyptic tantrums remains one of the great unsolved mysteries in stellar astrophysics. Some theories suggest the star's luminosity approaches the Eddington limit so closely that its radiation pressure literally blows its outer layers off in repeated, violent spasms. Others propose that deep within its core, strange modes of pulsation or the production of antimatter might trigger these colossal mass ejections. Whatever the cause, luminous blue variables like Eta Carinae demonstrate that for the most massive stars, death is not a single event, but a long, turbulent, and spectacularly violent process. Solitude is a rare luxury for the universe's giants. The vast majority of these colossal stars are born not alone, but locked in a gravitational dance with at least one companion, forming binary or multiple star systems. This cosmic partnership is far from peaceful. It is an intimate and often violent relationship that can completely rewrite a star's destiny. The key to this transformation lies in a process called mass transfer, a celestial theft that occurs when two stars orbit so closely that the gravitational pull of the larger, denser star can literally strip the outer layers from its companion. Imagine a cosmic vampire siphoning the very lifeblood of hydrogen from a neighboring sun to extend its own brilliant, fleeting existence. For the star receiving this stolen material, it is a form of stellar rejuvenation. A fresh infusion of hydrogen fuel falls onto its surface, reigniting fusion processes with a new ferocity and effectively resetting its evolutionary clock. This can turn an aging star back into a blazing blue youngster, dramatically altering its expected lifespan and its ultimate fate. But for the donor star, the consequences are catastrophic. It is left stripped and exposed, its hydrogen-rich envelope torn away to reveal its hot, helium-burning core prematurely. This process can create bizarre, naked stellar remnants like helium stars or Wolf-Rayet stars long before they would have naturally appeared. The most dramatic outcomes of this stellar cannibalism are some of the most exotic objects we observe in the cosmos. If the star receiving the mass is a dense remnant like a neutron star or a black hole, the infalling gas spirals in at near light speed, heating to millions of degrees and glowing with intense X-rays. We see these as X-ray binaries, where a tiny, city-sized neutron star brilliantly outshines its massive companion in high-energy light. On an even grander scale, if both stars in the binary are massive enough to form black holes, their gravitational tango can continue even after death. These binary black holes will slowly spiral inward over billions of years, eventually colliding in an event so powerful it ripples the very fabric of space-time, sending gravitational waves echoing across the universe. These stellar titans can become cosmic fugitives racing across the galaxy. We call them runaway stars, massive objects flung from their birthplaces at incredible speeds, some traveling at hundreds of thousands of kilometers per hour. There are two primary ways a star can be sentenced to this solitary exile. The first is a violent divorce. Imagine a binary system where two massive stars orbit one another. When the more massive one exhausts its fuel and explodes as a supernova, the sudden, asymmetric blast can literally kick the surviving partner away with tremendous force. It is like standing on a suddenly released catapult. The star is flung from the scene of the catastrophe, destined to wander the galaxy alone. The second mechanism is a gravitational mugging in a crowded star cluster. In these dense environments, stars are constantly engaging in close gravitational encounters. Sometimes, a particularly close pass between two or more stars can act like a slingshot, flinging one of them clear out of the cluster entirely. This dynamical ejection sends the star on a high-speed journey into the galactic void. A perfect example of this dramatic exile is Zeta Ophiuchi, a massive blue giant currently speeding through space. This star is not traveling through a vacuum, it is plowing through the thin interstellar medium. The result is a breathtaking spectacle, a colossal bow shockwave that glows in brilliant infrared light. Just as a speedboat creates a V-shaped wake in water, Zeta Ophiuchus' fierce stellar winds and radiation are compressing and heating the gas in front of it, forming a glowing arc that stretches across light years of space. This runaway star is a celestial nomad. Its brilliant bow shock a temporary monument to its violent expulsion and its lonely, high-speed journey through the cosmos. These ultimate fates are not arbitrary. They are governed by two of the most important numbers in all of physics. Deep within the equations that describe the deaths of stars, we find precise boundaries, cosmic checkpoints that dictate whether a star becomes a dense cinder or a bottomless pit. The first of these is the Chandrasekhar limit, named for the astrophysicist who discovered it. This limit, approximately 1.4 times the mass of our Sun, represents the maximum possible weight for a white dwarf star. A white dwarf is the exposed core of a star like our Sun, a dense sphere of carbon and oxygen supported by a quantum mechanical effect called electron degeneracy pressure. Think of it as a force created by the frantic motion of electrons being squeezed into an impossibly small space, a last-ditch rebellion against the crush of gravity. As long as the star's core remains below 1.4 solar masses, this electron pressure can hold firm, creating a stable, Earth-sized ember that will slowly cool over billions of years. But if the core is heavier, if it crosses that 1.4 threshold, electron degeneracy pressure shatters. The electrons are forced into protons, creating neutrons, and the core collapses catastrophically into a neutron star or beyond. This simple number is why a large percentage of stars in the universe end their lives in the brilliant flash of a Type Ia supernova, a thermonuclear explosion that occurs when a white dwarf steals just enough mass from a companion to push itself over this fatal edge. For neutron stars, there exists an even more extreme boundary, the Tolman-Oppenheimer-Volkoff limit. This is the theoretical maximum mass for a neutron star, estimated to be somewhere between 2 and 3 times the mass of our Sun. A neutron star is supported by neutron degeneracy pressure, an even more exotic version of the force that holds up a white dwarf. Here, it is the neutrons themselves that are packed together, creating a solid ball of nuclear matter so dense it represents the final possible stand of normal physics. If the collapsing core of a massive star exceeds this limit, perhaps because it was born with so much mass or because it accreted extra material, then even the incredible strength of a neutron star fails. There is no known force in the universe that can stop the collapse. The core continues its inward fall, vanishing completely to form a black hole. These two limits, the Chandrasekhar and the Tolman-Oppenheimer-Volkoff, are the universe's ultimate arbiters of stellar fate. They are the precise mathematical lines that separate the existence of a stable remnant from the creation of an absolute void. The violent death of a giant star echoes across space and time, but its birth has always been shrouded in mystery, hidden within thick, dark clouds of cosmic dust. For decades, our view into these stellar nurseries was like trying to observe a candle flickering behind a brick wall. The James Webb Space Telescope has utterly transformed that view. With its powerful infrared eyes, Webb does not see light, it sees heat, allowing it to peer straight through those obscuring dust clouds as if they were mere fog. We are now witnessing the formation of massive stars in their earliest, most violent stages with a clarity that was once pure science fiction. We can see the powerful jets erupting from infant stellar titans and watch as their fierce radiation begins to carve out vast cavities in the surrounding gas. But Webb's vision extends far beyond stellar cradles. By analyzing the specific infrared signatures of light, it can dissect the fierce stellar winds blowing from supergiants, measuring their speed and composition with incredible precision. This allows us to understand the dramatic mass loss that defines these stars' lives in real time. Perhaps most profoundly, Webb turns its gaze to the aftermath. It studies the glowing, complex chemistry within distant supernova remnants, identifying the specific elements forged in those cataclysmic explosions. By looking at galaxies billions of light-years away, Webb is effectively looking back in time, censusing the populations of massive stars in the infant universe. How did the first generations of these titans form in a cosmos of pure hydrogen and helium? The data streaming back from this incredible observatory are not just providing answers, they are fundamentally rewriting the story of cosmic dawn. Before the cosmos was filled with the rich chemistry we know today, the very first stars ignited in a universe of profound simplicity. These hypothetical objects, known as population 3 stars, were the true pioneers, forming from clouds of nothing but hydrogen and helium, the pristine elements forged in the Big Bang itself. Their existence was fundamentally different from any star we can observe today. In our modern universe, the presence of elements like carbon and oxygen allows a collapsing gas cloud to cool efficiently, radiating away heat and fragmenting into stars of many different sizes. But in that early, pure cosmos, there were no such cooling agents. The primordial gas could not shed its heat easily, and this led to a staggering consequence. The clouds collapsed into single, enormous clumps without breaking apart. The result was a generation of stellar titans on a scale we can barely comprehend. Each one of these first stars was likely a behemoth containing anywhere from 100 to 1,000 times the mass of our Sun. They were not just massive, they were truly monstrous, glowing with a ferocious blue-white intensity that had never before been seen. Their lives were as brief as they were spectacular. With such immense mass fueling a frantic fusion rate, they burned through their entire nuclear fuel supply in just a few million years. And their deaths were as unique as their birth. For the very largest of these primordial giants, their final act was not a core collapse supernova, but something even more total. They would have ended their lives as pair instability supernova, the same self-annihilating explosions we discussed earlier. In these universe-shaking blasts, the entire star would have been utterly vaporized, leaving behind no black hole or neutron star, just an expanding cloud of newly forged elements. This was the moment that changed everything. For the first time, the sterile cosmos was polluted with the seeds of complexity. The cataclysmic explosions of the first stars scattered the first carbon, the first oxygen, the first silicon, and the first iron across the void. This initial enrichment, though faint by today's standards, was the crucial first step. It provided the building blocks for the next generation of stars, the population 2 stars, which formed with a tiny trace of these new metals. Those stars, in turn, lived and died, further enriching the cosmic gas until finally, billions of years later, stars like our Sun and rocky planets like our Earth could form. We are the distant descendants of those first, unimaginable giants, our very existence made possible by their violent and brilliant sacrifice. Even the most brilliant flash in the cosmos can be a cosmic deception. Some of the most luminous stellar explosions ever recorded are not supernova at all, but a bizarre class of events known as supernova imposters. These are colossal eruptions from stars like luminous blue variables, violent tantrums that release a staggering amount of energy and light, momentarily rivaling the death of a true star. Yet when the glare fades, the star is still there. It survives, though profoundly scarred and forever changed by the experience. The most famous example is the great eruption of Eta Carinii we discussed earlier, an event in the 1840s that made it the second brightest star in the sky for years. At the time, if telescopes had been more powerful, astronomers might have classified it as a supernova, but Eta Carinii did not die. It merely threw a fit of epic proportions, ejecting vast amounts of its own mass to form the homunculus nebula. This phenomenon blurs the line between a dramatic outburst and a true stellar death, forcing astronomers to ask a critical question when they see a brilliant new point of light in a distant galaxy. Are we witnessing a star's final farewell, or is it simply screaming into the void? The existence of imposters challenges our most basic interpretations of stellar behavior. revealing that the lives of the most massive stars are punctuated by violent, non-lethal convulsions that are nearly as bright as their ultimate demise. A star's rotation is far more than a simple celestial pirouette. For a massive star, its spin is a fundamental force that can rewrite its entire life story. Most stars, including our Sun, rotate at a moderate pace, with their inner cores and outer envelopes spinning largely independently of one another. But when a massive star spins at a significant fraction of its breakup speed, something extraordinary happens. The ferocious centrifugal force and powerful internal currents it generates act like a colossal blender, churning the star's interior. This violent mixing does not just stir the surface, it dredges up freshly fused material from the core and carries it all the way to the surface, while simultaneously dragging fresh hydrogen fuel from the outer layers down into the burning heart of the star. This process of rotational mixing is a form of stellar rejuvenation. It constantly replenishes the core's fuel supply, preventing the buildup of helium ash that normally signals the beginning of the end. The result is a dramatically extended lifespan, allowing a rapidly spinning giant to burn for millions of years longer than an identical, slow-spinning star. Its surface composition becomes a bizarre and direct window into its core, rich with helium, nitrogen, and other elements that should be hidden deep within. These stars are known as chemically homogeneous, essentially mixed into a uniform composition from center to edge. Because they never develop the classic layered onion structure, they skip entire evolutionary phases that their slower spinning siblings must endure. Their ultimate fate is also transformed. Instead of collapsing through the traditional sequence of shells, a homogeneous star might fuse elements all the way to iron in a more uniform core, leading to a completely different kind of supernova explosion, one without a hydrogen envelope known as a type Ike. But the influence of spin does not stop at mixing. The centrifugal force at the equator of an extremely fast spinning star can become so powerful that it nearly counteracts gravity itself. This can cause the star to bulge outward into a distorted oblate spheroid, and in the most extreme cases, it can fling its own outer layers into space, forming a stable, glowing belt of gas orbiting the star known as a decretion disk. This is not an accretion disk pulling material in, but its opposite, a disk created by the star violently throwing material off. This rapid rotation, often a birthright from the chaotic collapse of its natal cloud, is a hidden variable, a secret key that unlocks alternate stellar destinies and creates some of the most unusual and powerful explosions in the cosmos. That ferocious spin we just discussed can transform a star's death into the single most powerful explosion in the modern universe. When a massive, rapidly rotating star reaches the end of its life, its core does not simply collapse into a black hole, it forms a cosmic particle accelerator of unimaginable power. This is the engine behind a long-duration gamma-ray burst, a flash of light so concentrated and energetic that, for a few fleeting seconds, it can outshine every star in 100 billion galaxies combined. The key to this cataclysm is the star's angular momentum, the same spin that mixed its interior. As the core collapses, all that rotational energy becomes focused. Instead of forming a neutron star, the core's mass is too great and it plummets directly into a black hole, but the infalling material does not simply vanish. It forms a superheated, magnetized disk of plasma, swirling around the newborn black hole at near light speed. The star's immense rotation funnels this chaos, launching two ultra-relativistic jets, like twin blasts from a celestial cannon, directly along the star's rotation axis. These jets are not fire, they are a soup of radiation and particles moving at 99.99% the speed of light. They are so focused and powerful that they can actually punch their way straight through the body of the star itself, bursting out of its poles in a matter of seconds. If you are standing in the path of one of these beams, you witness a gamma-ray burst, a torrent of the highest energy photons the universe can produce. But if you are viewing the star from the side, from anywhere outside the narrow cone of the jet, you might see nothing more than a relatively ordinary supernova. Our view of this cosmic violence is entirely a matter of perspective, a lethal lottery of alignment across the depths of space. But what if a star were to grow beyond any scale we have yet discussed, beyond even the primordial giants of the early cosmos? We now venture into the realm of pure theory, to a class of objects so immense it defies every convention of stellar life. These are the supermassive stars, hypothetical behemoths with masses ranging from tens of thousands to millions of times that of our Sun. They are not merely larger versions of the stars we know, they would be entities of an entirely different order, governed by a unique and self-destructive physics. In the chaotic conditions of the very early universe, where vast, pristine clouds of gas could collapse without fragmenting, such a monstrosity might have been possible. Its formation would have been a single, catastrophic event, an entire giant molecular cloud collapsing directly into a single, shining point. The internal structure of such a star would be unlike anything in the modern cosmos. Its immense weight would generate such intense radiation pressure that the entire star would be puffy and distended, more like a vast, low-density atmosphere than a compact ball of fire. It would shine with a ferocious, quivering light, trembling on the edge of stability, and its fate would be the most direct and absolute of all. A star like this would never experience the complex, layered fusion of its smaller cousins. It would burn hydrogen for a brief, brilliant period, perhaps only a few million years. But when its fuel was exhausted, there would be no rebound, no supernova, no glorious explosion to mark its passing. The radiation pressure that had been holding it up would vanish. With no outward force left to counter it, the star's own overwhelming gravity would win in an instant. The entire structure, all hundreds of thousands of solar masses of it, would simply fall inward. There would be no violent shockwave, no ejection of enriched material into space. It would be a silent, total collapse, a direct and unimpeded plunge straight through the event horizon. In a cosmic whisper, the star would vanish, leaving behind only a supermassive black hole. This theoretical fate provides a compelling solution to one of astronomy's greatest puzzles. How did the supermassive black holes at the hearts of galaxies, with masses of millions or even billions of suns, form so quickly after the Big Bang? If the first structures in the universe were these supermassive stars, their direct collapse would provide ready-made seeds, colossal black holes born fully formed, already massive enough to begin their growth into the galactic monsters we observe today. This rhythmic heartbeat in the sky is a direct consequence of stellar instability. For certain massive stars, their outer layers become a cosmic engine of pulsation, breathing in and out with a precise, predictable rhythm. These are the Cepheid variables, and they occupy a very special, narrow region on the Hertzsprung-Russell diagram known as the instability strip. This is not a random location. It is a precise zone where the star's internal conditions are perfectly tuned for oscillation. The driving force behind this stellar heartbeat is a layer of partially ionized helium. Think of this layer as a sophisticated heat engine, a built-in valve deep within the star's atmosphere. When the star is at its smallest and densest, this helium layer is compressed and heated. The intense energy rips electrons away from some of the helium atoms, a process known as ionization. This ionized gas becomes incredibly opaque, trapping the star's radiation like a thick blanket. The trapped heat increases the internal pressure, forcing the entire outer envelope of the star to expand dramatically. But as the star expands, it cools. The helium ions recapture their electrons, becoming transparent again. The radiation escapes, the internal pressure drops, and gravity seizes its chance. The star's outer layers fall back inward, only to be compressed and heated once more, restarting the entire cycle. This continuous, rhythmic dance between the forces of radiation and gravity causes the star to swell and shrink, its brightness rising and falling in a steady, luminous pulse. The true cosmic gift of these pulsating giants is the direct relationship between their pulse and their power. The longer it takes a Cepheid to complete one full cycle of brightening and dimming, the more intrinsically luminous it is. A Cepheid that pulses over a 10-day period is far brighter than one with a 2-day period. This period luminosity relationship transforms these stars into the universe's most reliable mile markers. When astronomers find a Cepheid variable in a distant galaxy, they simply measure its pulsation period. That period immediately tells them the star's true, absolute brightness. By comparing that known intrinsic brightness to how faint the star appears from Earth, they can calculate the distance with stunning accuracy. It was this very method that Edwin Hubble used to prove the Andromeda Galaxy was a separate island universe, forever shattering the notion that our Milky Way was all that existed. Every rhythmic pulse from these distant giants is a beacon, a cosmic lighthouse whose steady flash allows us to map the vast, empty expanses between the stars. V Canis Majoris redefines our very concept of a star's size. This is not a star of immense mass, but of incomprehensible volume, a red hypergiant so vast it dwarfs our entire solar system. If you were to place this celestial titan at the center of our own solar system, its searing, tenuous surface would not stop at the orbit of Earth or even Mars. It would stretch out past the asteroid belt, completely engulfing the giant planet Jupiter itself. Every planet from Mercury to Jupiter would be orbiting deep within its fiery, turbulent atmosphere. Yet for all its staggering scale, V Canis Majoris is surprisingly light. It holds only about 17 times the mass of our Sun, a fraction of the weight carried by true mass titans like R13601. This paradox reveals a star in its final, desperate old age, a bloated and unstable balloon on the verge of popping. Its immense size is a sign of profound weakness, not strength. It has exhausted the hydrogen fuel in its core and has swelled into a monstrous red hypergiant. Its outer layers now so distended and loosely bound that they are barely held by gravity. This instability is written across the space around it. The star is shrouded in a complex, beautiful nebula of its own making, a tangled web of gas and dust ejected over thousands of years. This is not a gentle stellar wind, but the evidence of colossal, eruptive mass loss, as if the star is coughing vast pieces of itself into the void. This spectacular nebula is the star's own funeral shroud, woven from the material it is shedding in its final millennia. Its fate is sealed. Within the next 100,000 years, a cosmic blink of an eye, the core of V Canis Majoris will finally collapse. It will then unleash a supernova explosion so brilliant it will be easily visible from Earth in our daytime sky. A final, dazzling farewell from one of the universe's most magnificent and ephemeral giants. The Eddington limit is not a passive boundary, it is a constant, violent negotiation. This theoretical ceiling dictates the maximum brightness a star can achieve before its own light becomes a weapon of self-destruction. The physics is a beautiful, terrifying tug of war. Every photon of light streaming from the star's core carries a tiny amount of momentum, creating an immense outward radiation pressure. For a star to remain stable, this outward push must perfectly balance the inward crush of its own gravity. But as a star grows more massive and luminous, this balance becomes increasingly precarious. When a star's luminosity approaches the Eddington limit, the radiation pressure becomes so overwhelmingly powerful that it starts to overpower gravity itself. It is like trying to build a sandcastle in the middle of a hurricane. The very force of the wind blows the sand away faster than you can pile it up. For the most massive stars, this is not a hypothetical scenario, it is the central drama of their existence. They are born so brilliant that they perpetually flirt with this cosmic speed limit. To avoid literally blowing themselves apart, they must constantly and violently shed their own mass through those ferocious stellar winds. This is not a gentle evaporation, it is a controlled explosion, a desperate bleeding of the star's own substance to keep the internal pressures from reaching a catastrophic climax. The furious stellar winds we observe screaming from stars like Eta Carinae are a direct consequence of this battle, the star's only way to vent its excess energy and cling to stability. This same fundamental limit also governs the behavior of matter falling onto the dead remnants of stars. When a black hole or neutron star pulls gas from a companion star, that material does not fall silently. As it spirals inward, it compresses and heats to millions of degrees, glowing with incredible intensity. This process of accretion can also approach the Eddington luminosity. The radiation pouring out from the hot gas can become so powerful that it pushes back against the incoming stream of matter, effectively turning off the black hole's own food supply. There is a maximum rate at which even a black hole can devour its surroundings, a rate set not by its appetite, but by the simple, universal physics of light pushing back against gravity. This elegant rule connects the violent lives of the brightest stars to the final feasts of the darkest objects in the cosmos. Iron may be the final element a star can forge through normal fusion, but the cosmic foundry does not shut down there. The creation of elements heavier than iron requires a completely different kind of alchemy, one that does not rely on the heat of a star's core, but on a relentless bombardment of subatomic particles. This is the realm of neutron capture, and it happens in two distinct ways, each leaving its own unique fingerprint on the periodic table. The first method is a slow, patient cook. Inside aging red giants and during the late stages of massive star evolution, free neutrons are available in a steady trickle. These neutrons are gradually captured by existing seed nuclei like iron. When a nucleus captures a neutron, it becomes a heavier isotope of the same element. If this new isotope is unstable, it will undergo radioactive decay, transforming a neutron into a proton and effectively stepping one element higher on the periodic table. This slow neutron capture process, or S process, is a methodical climb, building elements like strontium, barium, and lead one painstaking step at a time over thousands of years. It is the universe's master jeweler, carefully crafting a specific set of heavy elements in the relative calm before the stellar storm. But to create the very heaviest elements, the universe requires utter chaos. For gold, platinum, and uranium, a far more violent and rapid process is needed. This is the R process, or rapid neutron capture. It requires an environment so flooded with neutrons that atomic nuclei are bombarded before they have any chance to decay. Imagine trying to build a structure by having countless balls thrown at you faster than you can even process what you are catching. In this frantic environment, a single seed nucleus can swallow dozens of neutrons in a fraction of a second, rocketing up the periodic table to form extremely heavy, unstable isotopes. These bloated nuclei then rapidly decay into the stable, precious heavy elements we recognize. The incredible energy and density required for this process are thought to exist only in the most catastrophic events, like the collision of two neutron stars or the very heart of a core collapse supernova. In those fleeting moments, as two dead stars spiral into each other or as a star's core rebounds, a firestorm of neutrons is released, forging the universe's most precious treasures in a blinding flash. Every piece of gold on Earth was likely born in such a cataclysmic event, a relic of a violent merger that occurred billions of years before our solar system even existed. A planetary system around a massive star is a story written in vanishing ink. Any worlds that coalesce from the dusty disk surrounding a young giant are born into a hostile universe. From the moment the star's nuclear heart ignites, its planets face an unending assault. The star does not offer the gentle, life-giving warmth of a sun like our own. Instead, it bathes its entire system in a searing bath of ultraviolet radiation, a constant, high-energy glare capable of breaking apart the complex molecules that are the building blocks of life. Simultaneously, the star's fierce winds, a billion-mile-per-hour hurricane of charged particles, relentlessly scours the inner system, stripping away atmospheres and blasting the surfaces of any rocky worlds down to barren bedrock. This is not an environment that fosters delicate ecosystems. It is a forge that melts down planets before they can ever truly form. Imagine a world of bare, glowing rock, its skies torn away by the stellar gale, its surface baked under a blue-white sun that fills the sky. This is the only kind of planet that could survive for long in such a violent neighborhood. But even this stark existence is temporary, a brief prelude to an absolute ending. When the star finally exhausts its fuel and its core collapses, the resulting supernova explosion unleashes more energy in a few seconds than the star emitted over its entire multi-million-year life. For any surviving worlds, there is no defense. The flash of light alone delivers a lethal dose of radiation across light years. Then, the physical shockwave of expanding stellar debris arrives, traveling at tens of millions of kilometers per hour. This wave of incandescent gas does not gently push planets aside. It vaporizes them completely, shattering their atoms and blending their substance with the enriched material from the star's own corpse. The entire architecture of that planetary system is erased in an instant, its worlds reduced to a cloud of dust and gas, their atoms scattered into the void to one day become part of new stars, new nebulae, or perhaps in a much kinder system, a new world with a chance for life. Capturing the full story of a massive star's life is a uniquely human challenge. These titans are incredibly rare, scattered across the vast gulfs between galaxies. Finding one is like searching for a single specific grain of sand on all the beaches of Earth. Even when we locate them, they are often shrouded in the very cosmic dust that gave them birth, their brilliant light filtered and dimmed by the dense nebulae they call home. Our greatest obstacle, however, is time itself. A star like our Sun evolves over billions of years, a timescale that feels eternal to us. But a massive star lives and dies in just a few million years. While that is a cosmic blink, it is still an immense span from our human perspective. We have only been studying the stars with telescopes for a few centuries. This means we are like an audience arriving at the theater for a play that lasts 1,000 years. We might catch a single, fleeting scene, but we never witness the entire performance from beginning to end. We cannot watch a single star be born, mature, and explode. Instead, we must become cosmic detectives. We gather clues by observing thousands of different stars, each frozen at a single moment in its life cycle. We see a brilliant blue O-type star in a distant nebula and recognize it as an infant. We find a bloated red supergiant and mark it as an elder. We catalog the violent wolf-rayed stars and identify them as being in their final act. By stitching together these countless individual snapshots, we painstakingly assemble the complete biography of a massive star, a portrait pieced together from fragments of light across the entire galaxy. The journey to stardom follows different paths for the cosmic aristocracy. For a modest star like our Sun, the path to maturity is a long, slow descent. After its initial collapse from a gas cloud, a young, low-mass star enters a prolonged phase known as the Hayashi track. It is a bloated, cool protostar, glowing a deep red as it gradually contracts over tens of millions of years, slowly heating up until its core is finally hot enough to ignite sustained hydrogen fusion. This is a star's extended childhood, a patient journey toward the main sequence. But for a massive star, there is no such leisurely stroll. Its formation is a headlong rush, a brutal and immediate confrontation with its own destiny. From the moment a clump of gas begins to collapse into a future giant, the process is one of overwhelming force. The sheer weight of infalling material creates such immense pressure in the core that temperatures skyrocket at a breathtaking pace. There is no time for a prolonged, bloated infancy. Hydrogen fusion ignites in a furious flash while the star is still actively accreting mass from its surroundings. It essentially leaps onto the main sequence, fully formed and burning with ferocious intensity from its very first breath. This is the fundamental difference between a gentle ember and a celestial inferno. One matures with patience, the other is born in a state of brilliant, violent urgency, its entire life a race against the very forces that gave it light. Magnetic fields bind these stellar giants with invisible chains of immense power. While we often think of a star's surface as a uniform inferno, the presence of a strong, organized magnetic field can transform it into a landscape of dramatic extremes. These are not the tangled, dynamic fields of our Sun, but vast, fossilized structures often locked in a simple dipole shape, like a colossal bar magnet embedded within the star itself. This magnetic architecture exerts a profound control over the star's most violent processes. The fierce stellar winds, which normally stream outward in a spherical hurricane, are forced to follow the magnetic field lines. They funnel away from the magnetic equator and instead erupt with concentrated force from the magnetic poles, creating two colossal geysers of superheated gas. This channeling dramatically focuses the star's mass loss, sculpting its immediate environment and shaping the nebulae that will eventually surround its remnant. These magnetic fields also leave a clear, if bizarre, mark on the star's visible surface. They can trap searingly hot plasma, creating enormous, persistent bright spots that rotate into and out of our view. Instead of a steady, uniform glow, the star's light pulses rhythmically as these brilliant magnetic anchors sweep around, offering astronomers a clear signal of the powerful, hidden forces at work within. The origin of these fields is a subject of intense debate. Were they inherited from the star's natal cloud, frozen into the star during its chaotic collapse? Or are they generated by fierce internal dynamos, driven by the incredible shear between different layers of the star spinning at different rates? Whatever their source, their influence is undeniable, acting as a master regulator on the star's life. They can act as a braking mechanism, transferring the star's rotational energy out into space and slowing its furious spin over time. This magnetic braking directly impacts how the star mixes its internal fuel and ultimately the path it will take to its final, cataclysmic death. The presence or absence of a strong magnetic field is a hidden variable that can steer two otherwise identical stars toward completely different destinies, a silent puppeteer guiding the fate of a giant. Rho Cassiopeiae is a star that should not exist. It belongs to a class of stellar anomalies known as yellow hypergiants, cosmic behemoths so unstable they barely cling to life. Imagine a star caught in a cosmic tug-of-war, perpetually trembling on the edge of self-destruction. These rare objects occupy a precarious and nearly empty region on the Hertzsprung-Russell diagram, a zone of extreme instability between the brilliant blue supergiants and the vast, cool red supergiants. They are not comfortably settled in their evolution, but are in a frantic, fleeting transition, rapidly changing their identity before our eyes. A yellow hypergiant is essentially a star in the midst of a catastrophic identity crisis. It has exhausted the hydrogen in its core and is now burning helium, causing its outer layers to swell and cool. But this expansion is not a gentle process. The star's immense radiation pressure battles against its own gravity in a violent, unstable equilibrium. The result is a star that throbs and convulses, its outer layers so loosely bound that they can be hurled into space in colossal eruptions. Rho Cassiopeiae itself has demonstrated this volatility in spectacular fashion. In a single observed eruption, it ejected an amount of material equal to 1% of our entire Sun's mass. That is 10,000 times the mass of Earth, blown off in a stellar tantrum that briefly made it one of the most luminous stars in the entire galaxy. This is not a gentle stellar wind, it is a star violently shedding its own skin. These eruptions are the star's desperate attempt to find stability, a dramatic weight loss program on a cosmic scale. Each outburst strips away the star's outer hydrogen envelope, pulling it back from its journey toward becoming a red supergiant and revealing the hotter, helium-burning layers beneath. This forces the star to heat up and turn blue again, only for the cycle to repeat. This back-and-forth struggle provides astronomers with a priceless window into the final, chaotic chapters of a massive star's life. By studying the violent pulsations and mass loss of yellow hypergiants, we witness the real-time death throes of a giant, a preview of the supernova explosion that will inevitably tear it apart. The death of a giant does more than just scatter new elements into the void. It floods the galaxy with a ghostly, high-energy rain. These are cosmic rays, a mysterious form of radiation that constantly bombards our planet from the depths of space. They are not rays of light at all, but atomic shrapnel consisting mostly of protons and atomic nuclei hurtling through the void at nearly the speed of light. For decades, the origin of these incredibly energetic particles was one of astronomy's greatest puzzles. Where in the universe could nature possibly build such a powerful particle accelerator? The answer lies in the expanding fury of a supernova remnant. The colossal shockwave from the explosion, a wall of incandescent gas and magnetic fields traveling at millions of kilometers per hour, creates the perfect natural engine for this task. As this shock front plows through the interstellar medium, it scoops up stray protons and atomic nuclei from the surrounding space. These particles become trapped by the turbulent magnetic fields tangled within the shock, bouncing back and forth across the advancing wave front like rubber balls in a cosmic paddleboard. With each crossing, they gain a tremendous burst of energy, accelerated faster and faster until they are eventually flung out into the galaxy, traveling at a significant fraction of light speed. This process, known as diffusive shock acceleration, turns the supernova remnant into a celestial synchrotron, operating on a scale far beyond anything we could ever build on Earth. Every second, thousands of these cosmic ray particles pass harmlessly through your body, a silent, invisible drizzle that is the direct legacy of stellar cataclysms that occurred millions of years ago. They are the final, energetic echoes of dead stars, a testament to the fact that a star's influence extends long after its light has faded from view. Our cosmic detective story is about to gain powerful new chapters. The next generation of observatories, both on the ground and in space, will transform our view of these stellar titans from a collection of still images into a high-definition movie. The Vera C. Rubin Observatory, set to begin its monumental survey of the sky, will not merely look at the universe, it will watch it. Every few nights, it will capture the entire visible sky, creating a time-lapse of the cosmos over a decade. This relentless gaze will allow us to catch supernova in the act of exploding, spotting the first brilliant flash of light from a dying giant within hours of its detonation. For the first time, we will witness the earliest moments of these cataclysms, understanding the final, desperate signals a star sends before it tears itself apart. But light is only one part of the narrative. The universe also speaks through ripples in the fabric of spacetime itself. The global network of gravitational wave detectors, including LIGO, Virgo, and CAGRA, is listening for the silent, violent mergers of the remnants these stars leave behind. When two black holes or two neutron stars spiral into each other, they do not emit a flash of light, they shake the cosmos. These observatories feel that shake, detecting the subtle stretching and squeezing of space as the two massive objects collide. Each merger is a direct message from beyond the grave, revealing the end result of stellar lives that began millions of years ago. By combining what we see with our eyes and what we feel with these incredible instruments, we are opening multiple windows onto the same epic story. We will not only find more of these rare, massive stars, we will follow their entire life cycle, from their turbulent birth in dusty nebulae to their final, silent dance of death. The coming era of astronomy promises to turn these celestial titans from distant, enigmatic figures into characters whose full biographies we can finally read. Our very existence is a consequence of these ancient stellar deaths. This profound connection between our own lives and the demise of long-vanished giants is crystallized in a powerful philosophical idea known as the anthropic principle. In its simplest form, it suggests that the universe we observe must be compatible with the existence of conscious life that observes it. At first glance, this might sound circular, but when applied to the cosmos, it reveals a chain of necessity so precise it is humbling. Consider the fundamental ingredients for a planet like Earth, for the chemistry of life itself. You need carbon to form complex molecules. You need oxygen to breathe and to create water. You need iron for a planetary core that generates a protective magnetic field. You need calcium for bones and phosphorus for DNA. None of these elements were present in the newborn universe after the Big Bang. The cosmos began with only the simplest elements, hydrogen and helium. For hundreds of millions of years, there were no planets, no rocks, and no possibility for life as we know it. The universe had to forge these heavier elements, and the only cauldrons hot enough and powerful enough to do so were the cores of massive stars and their subsequent supernova explosions. This means the universe had to develop the specific physical laws that allow for the formation of these stellar titans. The strength of gravity, the force of nuclear interactions, the very mass limits of stars, all had to be precisely tuned to create the conditions where these cosmic forges could operate. If gravity were slightly weaker, massive stars might not form at all. If the nuclear force were slightly different, carbon might not be stable, and life based on carbon chemistry would be impossible. We are not merely living in a universe that happens to have massive stars. We are living in a universe that produced massive stars and therefore could eventually produce us. Every time you feel the solid ground beneath your feet, you are touching atoms fused in a star that died before our sun was even born. Every breath you take fills your lungs with oxygen that was blasted into the galaxy by a supernova. The iron in your blood was once the final, silent killer in the heart of a giant, a star that lived a short, violent life so that billions of years later you could be here to ponder its story. We are not just in the universe is in us. We are stardust given consciousness, the universe's way of looking back on itself and understanding the beautiful, violent processes that made its own existence possible. This stellar disappearance act presents one of modern astronomy's most intriguing puzzles. Our theories of stellar evolution provide a clear roadmap for a massive star's final years. After its brilliant blue phase, it should swell into a vast, cool red supergiant, a stage that ought to last for a substantial portion of its final 100,000 years. Given the sheer number of massive stars in a galaxy like our own, we should be able to point our telescopes at the sky and see dozens of these bloated, aging giants on the very brink of collapse. Yet when we look, we find almost none. These pre-supernova red supergiants are conspicuously absent, as if they have quietly vanished just before their final, dramatic exit. The stars that do explode as supernova often show no trace of the thick hydrogen envelope that characterizes a red supergiant. So where do they go? This missing red supergiant problem suggests our understanding of a star's final days is fundamentally incomplete. It appears that many massive stars undergo a rapid, dramatic transformation shortly before they die. Instead of exploding as a predictable red supergiant, they might engage in a final, violent outburst that strips away their entire outer hydrogen shell. This would leave behind a hotter, more compact star, like a Wolf-Rayet star, which then explodes just a short time later. We are effectively missing the final scene of the play because the star makes a sudden, last-minute costume change backstage. This hidden metamorphosis could be driven by a final, desperate surge of nuclear burning in the STR Chinese letter layers, triggering colossal pulsations that eject the star's own atmosphere into space. Another possibility is that the star's core becomes unstable in a way we do not yet fully understand, sending powerful waves through the star that literally blow its outer layers away. Whatever the cause, this cosmic sleight of hand means we are often watching for the wrong kind of star in the moments before a supernova. The universe is reminding us that even the most well-understood life cycles can hold secret final chapters, written in invisible ink until the very moment they are revealed by a flash of light that outshines entire galaxies. Their immense gravity makes them the undisputed rulers of their stellar kingdoms. Within a young star cluster, a single massive star or a small group of them will hold sway over hundreds or even thousands of their smaller, sun-like siblings. Their sheer mass defines the cluster's very heart, creating the deepest part of the gravitational well that binds every other star in place. This dominance is not a gentle leadership, it is an absolute monarchy built on pure gravitational force. The orbits of all the smaller stars are dictated by the presence of these central titans, but this rigid order contains the seeds of its own destruction. When one of these monarchs reaches the end of its life, its death is rarely a quiet, symmetrical event. The supernova explosion is often lopsided, a catastrophic detonation that can kick the collapsing core like a cosmic rifle shot. This supernova kick imparts a tremendous and sudden burst of energy to the entire cluster system. It is the equivalent of removing the central pillar from a grand building. The cluster's delicate gravitational balance is shattered. The explosive energy injected by the supernova, combined with the sudden loss of the massive star's anchoring gravity, can fling stars in every direction. In some cases, this violent event provides enough of a push to overcome the cluster's own gravity entirely. The cluster, once a tightly bound family of stars, becomes unbound. Its stellar members, from middleweight stars down to tiny red dwarfs, are sent scattering into the vast, empty tracts of the galactic disk, destined to live out their long lives as solitary wanderers. Many of the isolated stars we see in the Milky Way's field may in fact be refugees from such ancient cluster disasters, their origins lost to time but written in the trajectories they followed after being violently evicted from their childhood homes. Astronomers can listen to the heartbeat of a galaxy by counting its supernova. This rhythm, known as the supernova rate, tells a profound story about a galaxy's past, present, and future. It is not a random statistic, but a direct measure of a galaxy's vitality and its capacity for change. To calculate this rate, scientists begin with a cosmic census, meticulously cataloging the population of massive stars within a galaxy. Since these titans are the only stars that end their lives in core collapse supernova, their numbers directly predict the frequency of these brilliant explosions. By understanding the lifespans of these different stellar classes, from a short-lived 20 solar mass star to a slightly longer-lived 10 solar mass star, astronomers can build a timeline of expected stellar deaths. This allows them to estimate how often, on average, a galaxy should light up with a new supernova. This number is far more than just a count. It is a crucial parameter that reveals the intensity of a galaxy's ongoing chemical enrichment. A high supernova rate means the galaxy is being rapidly seeded with heavy elements, building the raw materials for future rocky planets and potentially life. Simultaneously, it measures the ferocity of the feedback cycle. Every supernova blast injects colossal energy into the interstellar medium, heating the gas and driving powerful galactic winds. This can compress some clouds to birth new stars while blowing others apart, creating a self-regulating system that ultimately dictates the galaxy's star formation efficiency. The character of this stellar rhythm changes dramatically depending on the galaxy. A grand spiral galaxy like our own Milky Way, with its steady but modest star formation, experiences a core collapse supernova roughly once every 50 years. In contrast, irregular galaxies, often small and chaotic, can have bursts of frantic activity. But the true drums of war beat in starburst galaxies, where entire regions are convulsing with the birth of massive stars. In these cosmic cauldrons, the supernova rate can be 100 times higher than in the Milky Way, with multiple stars exploding every century. This relentless barrage of explosions drives phenomenal outflows of gas, shaping the galaxy's destiny on a breathtaking scale. The supernova rate is the pulse of galactic evolution, a slow, steady beat in some and a frantic, explosive rhythm in others, each telling the story of how stars live, die, and reshape their cosmic homes. These tiny galaxies are cosmic time capsules, offering a direct window into the universe's chaotic youth. Known as green P galaxies, they appear in our telescopes as small, faint, and remarkably compact objects glowing with a distinct greenish hue. This unusual color is not from green stars, but a telltale signature of their extreme nature. Their light is overwhelmingly dominated by the intense emission from vast clouds of oxygen gas that have been violently ionized. And the only power source fierce enough to cause such a brilliant, specific glow is a tremendous population of newborn massive stars. A green P galaxy is essentially a stellar nursery on a galactic scale, a place where star formation is not just happening, but erupting in an almost uncontrolled frenzy. Within these small domains, the rate of star birth is staggering, up to 10 times higher than in a normal galaxy like our Milky Way. Yet all this ferocious activity is crammed into a region a tiny fraction of the size. This creates an environment utterly dominated by the life cycle of massive stars. Imagine an entire galaxy that resembles the core of the Tarantula Nebula, where massive stars are born, live, and die in a continuous, deafening roar. Their fierce radiation and powerful winds churn the galactic gas, and their frequent supernova explosions blast material outward, shaping the entire ecosystem. By studying these green Ps, we are witnessing a mode of galactic life that was commonplace billions of years ago, during the cosmos's most fertile period of star birth. They are living fossils, showing us a universe where massive stars were not just inhabitants, but the undisputed architects of their galactic homes. The final second of a star's life is a frantic, invisible drama. As the iron core collapses into a city-sized ball of neutrons, it becomes a furnace for the most elusive particles in the universe. In this brief, unimaginable moment, the core generates more neutrinos than there are stars in the observable universe. These ghostly particles, which normally pass through entire planets without a single interaction, are suddenly produced in such stupefying densities that they become trapped within the maelstrom. For a tenth of a second, the core is a seething soup of neutrons, protons, and neutrinos, all battling for dominance. It is the neutrinos that ultimately carry the star's final message, fleeing the catastrophe with 99% of the star's gravitational binding energy. This is the ultimate cosmic theft, a silent robbery of energy on an unimaginable scale. Yet for all their power, these neutrinos are not the killers. They are the potential saviors, the central mystery, the grand unsolved problem of the supernova mechanism lies in what happens next. The initial shockwave born from the core's rebound stalls. It is like a piston trying to push through an impossibly thick wall of infalling star stuff. It loses energy, becoming a standing shock, unable to move outward. For milliseconds, the explosion hangs in the balance, with the star's outer layers poised to fall onto the newborn neutron star and form a black hole. The question is, what revives this stalled shock and drives the explosion? The leading theory points back to those trapped neutrinos. We believe that a small fraction of them, just a single percent, deposit their colossal energy into the material just behind the shock, reheating it and reigniting the blast like a cosmic bellows. But the simulations are not yet perfect. Capturing the complex ballet of neutrinos, magnetic fields, and violent fluid motions in 3 dimensions pushes the world's most powerful supercomputers to their absolute limits. Sometimes the models explode, and sometimes they do not. This lingering uncertainty means we still do not fully know the final trigger for the universe's most common brilliant death. The last second of a giant's life holds a secret that the brightest minds and most powerful machines on Earth are still striving to unlock. That brilliant flash of a dying star is not a uniform signal. It arrives with a specific chemical fingerprint, a cosmic autopsy report that tells us exactly what kind of giant just met its end. This is the world of supernova classification, where astronomers act as celestial detectives, reading the light from these explosions to reconstruct the final moments of the star that produced it. The most common supernova from a massive star is the Type II. When we split its light into a spectrum, we see the clear, dark absorption lines of hydrogen. This tells a simple story. The star that exploded was a red supergiant, a vast, bloated giant that still held onto its thick, hydrogen-rich outer envelope right up until its core collapsed. The entire structure, from its hydrogen skin to its iron heart, was blasted into space, and the presence of that hydrogen leaves its unmistakable mark on the light. But sometimes the evidence tells a different, more violent tale. We see a supernova with all the power of a core collapse, but its spectrum is missing those hydrogen lines entirely. This is a Type 1b supernova. Its light reveals the signature of helium, but no hydrogen. The forensic conclusion is stark. Before this star ever exploded, something had already ripped away its entire hydrogen envelope, exposing the deeper layer of helium beneath. The final supernova in this family, the Type 1c, presents an even more extreme case. Its spectrum shows neither hydrogen nor helium. It is a star that has been stripped down to its bare bones, its outer layers completely peeled away to reveal the heavy element core beneath. These differences are not random. They are a direct and tragic record of the star's life story. A star might lose its hydrogen shroud through its own ferocious stellar winds, which over millions of years can blow its outer atmosphere clean away. More dramatically, if the star was locked in a tight binary system, its companion could have acted as a gravitational thief, siphoning off the hydrogen envelope and leaving a naked, helium-burning core to explode. The type of supernova we see is a final message, a last testament that reveals whether the star died alone and fully dressed, or was stripped and exposed by a companion or its own furious power before its final, brilliant demise. The hunt for a pair instability supernova is a search for a ghost, the spectral echo of the universe's first and most monstrous stars. Astronomers are scanning the skies for a specific, brilliant signature, a supernova so bright and so enduring it defies all conventional explanation. This would be the final, confirming evidence that stars can indeed grow to such immense sizes that they annihilate themselves completely. A leading candidate that sent a jolt of excitement through the astrophysics community was a supernova designated SN 2007b. Discovered in a small, faint dwarf galaxy, this was no ordinary stellar explosion. It shone with a peak luminosity 10 times brighter than a typical core collapse supernova, and its light curve faded with an agonizing slowness, remaining visible for over 1 year. This prolonged brilliance is a key clue. It suggests the explosion was powered by the radioactive decay of a colossal amount of nickel-56, an isotope forged in incredible quantities during a pair instability event. The sheer scale of SN 2007b points to a progenitor star that was a true behemoth, likely born with a mass around 200 times that of our Sun. While the evidence is compelling, the scientific process demands caution. Some researchers have proposed alternative models where a more conventionally sized star, if it was spinning extremely fast or had a unique chemical composition, might mimic some aspects of a pair instability blast. The hunt, therefore, continues, confirming the detection of such an event would do more than just add a new class of explosion to our catalogues. It would be a direct window into the population, 3 stars we theorize about, those primordial giants made of pure hydrogen and helium. Finding their modern-day descendants would prove that the physical conditions to create such unimaginable stellar titans did indeed exist, not just in the early cosmos, but potentially in rare pockets of the modern universe. It would confirm that the most total self-sacrifice a star can make is not just a theoretical idea, but a spectacular, observable fact. A star's death is never truly final. The black holes and neutron stars left behind by these cosmic giants will become the universe's longest-lasting monuments, solitary wanderers adrift in an ever-darkening cosmos. Their journey begins in the chaotic aftermath of the supernova that birthed them. The violent, asymmetric kick from that explosion can send them racing across the galaxy at tremendous speeds, becoming runaway remnants on a voyage with no destination. For trillions of years, these dark cinders will orbit the fading core of the Milky Way, their path slowly decaying as they lose energy through gravitational waves. Most will travel in profound isolation, their immense gravity hidden in the perfect blackness of space. Yet chance encounters will occasionally break their solitude. A rogue black hole might drift through a molecular cloud, its gravity pulling in wisps of gas. As this material spirals inward, it would compress and heat to millions of degrees, flaring with a brief, brilliant X-ray glow against the eternal night. In the dense stellar graveyards of ancient globular clusters, two neutron stars might finally complete a gravitational dance begun billions of years earlier. Circling each other at a significant fraction of light speed, their inevitable merger would create a final, spectacular flash of light and a thunderclap of gravitational waves, forging heavy elements like gold and platinum before vanishing into a single, more massive black hole. This slow, sporadic accretion and these rare, violent mergers will be the last major sources of luminosity in the cosmos. Long after the last red dwarf has cooled into a black dwarf and the galactic disks have faded into darkness, these remnants will still be there. Even the phenomenal timescales of stellar evolution are but a prologue to their epic story. Over durations that make the current age of the universe seem like a single breath, a process known as proton decay may slowly evaporate the remaining normal matter, including the dead cinders of white dwarfs and the cold, dense spheres of neutron stars. But the black holes will endure, their mass and gravity seemingly eternal. Yet, according to the subtle predictions of quantum mechanics, even they are not forever. Through a phenomenon called Hawking radiation, a supermassive black hole will gradually leak its mass away into the void, a process so slow it would take a googol of years, a one followed by 100 zeros. In the absolute farthest future, when the cosmos is an unimaginably cold, dark, and empty expanse, the final act of the most massive stellar remnants will be a silent, slow-motion evaporation, a whisper of radiation as the last black hole dissolves into nothingness. The legacy of the giants, which began in a blaze of light and sound, will end in the deepest, most profound silence imaginable. From their explosive births to their self-destructing finales, these stellar titans live by a creed of beautiful violence. They are the universe's great alchemists, forging the very elements of life in their cores and scattering them across the cosmos in their dying breaths. We have journeyed from the crushing limits of their formation to the exotic remnants they leave behind, from spinning pulsars to silent black holes. We have seen how their ferocious energy sculpts entire galaxies, triggering new star birth even as they blow away the cradles of future suns. This is the grand cycle of cosmic recycling, a story written in stardust. Every atom of oxygen in the air you breathe, every particle of iron in your blood, was once part of a star that lived fast and died young billions of years ago. You are not merely a passive observer of this distant drama. You are a living collection of its echoes, a testament to the universe's capacity to create beauty from chaos. The next time you find yourself beneath a dark sky, look up, see not just points of light but the brilliant, fleeting lives of distant suns. See the ghostly nebulae that are both their cradles and their graves. Let that vast, silent spectacle remind you of your own profound connection to the cosmos. We would love to hear which of these 50 facts reshaped your understanding of the universe, so share your favorite discovery in the comments below.